Hello, everyone. Welcome to today's session on geometry and topology. Our first speaker is Ciprian Manolescu from the University of California, Los Angeles, and he'll speak on homology, cobordism, and triangulations.
Thank you for the invitation. I'm delighted to speak here at the ICM. I will talk about some recent progress on understanding the homology cobordism group and also its applications to triangulations of manifolds. Okay, so let me start with triangulations. Recall that a triangulation of a topological space X is a homeomorphism from X to a simplicial complex. So the first interesting question was raised by Poincaré in his analysis Citrus 2 in 1899, where he asked, does every smooth manifold admit a triangulation? Well, not quite in this language, and actually he even tried to give a proof, but it wasn't fully rigorous. Still, the answer is yes. This was proved rigorously in the 40s by Cairns and Whitehead, and in fact, more is true. So every smooth manifold has an essentially unique piecewise linear structure, and therefore it's triangulable. So, okay, I will get back to PL structures soon. Another interesting question is you can weaken the hypothesis and ask, does every topological manifold admit a triangulation? So this was asked by Kneser in 1924. And there are actually two versions of this question. So you can ask about arbitrary triangulations if they exist, or you can ask about the more natural PL or combinatorial triangulations, which come from PL structures. So, all right, so now let me give the definition. A triangulation is called combinatorial or PL if the link of every vertex is PL homeomorphic to a sphere. So the link is, well, you take the vertex, you take all the simplices that contain the vertex, you take the closure, and then you remove the simplices that contain the closure, so that contain the point. So basically you look at the boundary, and if that's a sphere, yeah, we say that this is a PL triangulation. Notice that if that's the case, then the underlying space has to be a manifold, because locally it looks like the cone on a sphere, which is Rn. And it turns out that PL triangulations are equivalent to PL structures on the manifold. So a PL structure is just an atlas of charts, such that the transition maps are piecewise linear. And yeah, basically having one of those is the same as having a PL triangulation up to subdivision and isomorphism. However, manifolds can also have non-PL triangulations. This was not clear for a long time, but in the 70s, people figured out that it is possible. So the example is, one example is the double suspension of a homology sphere, of a non-trivial homology sphere, where it's not simply connected. So let's say we take Poincaré sphere, or any other homology sphere, non-trivial. And okay, so let's say it's triangulated. You can take the suspension, double cones on each simplex, and that gives you a triangulated space. That's actually not a manifold, because it looks like, around here, it looks like the cone on a non-simply connected space. But what's interesting is that if you do it again, so then you get a double suspension, this is actually homeomorphic to the sphere of dimension 2 higher. So this is a non-trivial result to prove this homeomorphism. It was proved by Edwards and Cannon in the 70s. So this gives you a triangulation of the n+2 dimensional sphere, but the link of this vertex is this sigma m, which is not a manifold. So even though the space itself is a manifold, the triangulation is not PL. Okay, so let me go over the classification of PL triangulations first on topological manifolds. So in dimension 3, there's nothing too interesting happening. Every manifold has a unique smooth and PL structure. But in dimension 5, there was some interesting work in the 60s, starting with surgery theory. Well, it built up on the work of Sullivan and Casson, and then Kirby and Seiberg proved this theorem. So they showed that there exist non-PL manifolds, topological manifolds that don't have PL structure, and in fact they characterized which ones have PL structures by an obstruction class in H4 of M with Z-2 coefficients. So this is called the Kirby-Seiberg invariant, and it's something you can associate to every topological manifold, and the manifold is PL if and only if this class vanishes. Okay, and furthermore, they show that if they exist, then PL structures are classified by elements in H upper 3 of M with Z-2 coefficients. And this implies the failure of the famous Hauptvermutung for manifolds. So the Hauptvermutung was the conjecture that every two triangulations of a space admit a common subdivision up to isomorphism. And Milnor found counterexamples first, but they were not manifolds. But from this, you can actually show that if the manifold has non-trivial H3 with Z-2 coefficients, then it admits triangulations that don't have a common subdivision. So, all right, so then there's also dimension 4. Dimension 4 is the most complicated in topology. And by the work of Donaldson and Friedman in the 80s, what happens is that actually, smooth structures may not exist and may not be unique, and smooth is the same as PL in dimension 4. But the classification is, it's unknown at the moment. There are results based on gauge theory, but we don't have such a nice classification of PL structures as in dimension greater or equal than 5. Okay, so now let me talk about the existence of arbitrary triangulations on topological manifolds. And here, the first progress was in dimension, in dimension less than 4, everything is straightforward. There's, there are smooth structures and PL structures and triangulations, but in dimension 4, following the work of Friedman, Casson proved that the E8 manifold is non-triangulable. So there exist topological manifolds that don't have any triangulations. This left open the case of dimension greater or equal than 5. And there was some work in the 70s based on the following idea. I mean, I'm gonna list the results, but just to, they look kind of strange. So just to give you the idea, you look at the links of simplices in the manifold. So if it has a triangulation, you can also take a simplex and look at the simplices that contain it and the boundary of that. That's called the link. And these turn out to be, in PL triangulations, these are spheres, but in general, they may not be spheres, but they are always homology spheres. So it turns out that many questions about triangulations can be rephrased in terms of a group that's made out of homology spheres. And this is called the homology cobordism group. So let me tell you what this is. It's an abelian group, and the generators are PL homology spheres divided by an equivalence relation where two manifolds are the same, are equivalent if there exists a cobordism between them such that the relative homology is 0. So basically it looks like a cylinder homologically. And I wrote here W4 because this group is only interesting in dimension 3. So it turns out that the group is trivial for n different from 3. And yes, but in dimension 3 it is non-trivial. Okay, so now let's talk about the three-dimensional homology cobordism group. So how can we prove that it's non-trivial? The first observation is that although I defined it in terms of piecewise linear manifolds and piecewise linear cobordisms, but since we're in dimension 3 and 4, the PL and smooth categories are the same, so we can just work with smooth manifolds and smooth cobordisms. And then we have, the first thing we have is the Ruffling homomorphism. So this is a classical invariant of a homology sphere. It gives a homomorphism from this group to Z mod 2, and the definition is you take the signature of a spin smooth 4 manifold with boundary Y, and you divide by 8, and then take it mod 2. So it turns out, I mean, the signature of a unimodular form, if it's even, because the manifold is spin, then it's divisible by 8. And furthermore, it turns out that this quantity, mod 2, it does not depend on W. So for example, mu of S3 is 0. This was the classical Ruffling theorem. But mu of the Poincare sphere is 1, because the Poincare sphere bounds the E8 plumbing, and that has signature 8. So this shows that this homomorphism is surjective, and that implies that theta 3z is non-trivial. So for a long time, this was all that was known about the group. But then with the advent of gauge theory in the 90s, it was basically using the Yang-Mills equations. It was shown that theta 3z has a Z infinity subgroup. This was a theorem of Furuta and Fintuschel-Stern. And also it has a Z summand. Having a summand, it's stronger than having a subgroup. So yes, so far we just know that there's a Z summand. This was a result of Freushoff. But there are still plenty of interesting questions. So does it have torsion? Does it have a Z infinity summand? What is it? Is it Z infinity, or maybe Z infinity plus Z mod 2 infinity? We don't know. In principle, as far as we know, it could be Z plus Q infinity. But we'll see. Okay, so now let's talk about, let's go back to triangulations of manifolds in dimensions greater or equal than 5. So, yes, so the analogs of the results of Kirby and Seiberg were found by Galuski, Stern, and Matsumoto in the 70s. And they are in terms of this homology, of this homology cobordism group and the Ruffling homomorphism. So, first of all, they show that there exist non-triangulable manifolds in dimension greater or equal than 5, if and only if this exact sequence does not split. So this is theta 3z and the Ruffling homomorphism to Z mod 2, and yes, and the kernel. So it was an open question for a long time if it doesn't split, and I proved in 2013 that it doesn't. So non-triangulable manifolds exist. So what does it mean that it doesn't split? It means that there's no map this way from Z mod 2 to theta 3z, meaning, well, what would be the image of 1 in here? It would be some homology sphere that's 2 torsion because it comes from Z mod 2, and the Ruffling homomorphism should be 1 on that. So this is a result about the homology cobordism group and the Ruffling homomorphism. There's no 2 torsion with mu equals 1. Furthermore, then you can ask about about which manifolds are triangulable, and Galuski, Stern, and Matsumoto also figured this out. So they proved that such a manifold of dimension at least 5 is triangulable if and only if a certain obstruction is 0 in H5 of M with values in kernel of mu. So this is kind of an analog of the Kirby-Seiberg result about that element in H4 of M Z mod 2. And in fact, this is exactly the Bachstein homomorphism of the Kirby-Seiberg invariant coming from this exact sequence. But, okay, this result is a little unsatisfying because this group is very complicated. In fact, we don't know what it is because we don't know what theta 3z is, but we know that it's infinitely generated. So it's a complicated group, and What would be nice is if we can find a simpler obstruction, and in fact, one can show that you can replace this with an equivalent obstruction in H5 of M's with Z coefficients if we knew that theta 3Z had no torsion with mu equals 1. So I proved that there's no 2 torsion with mu equals 1, but in principle there could be 4 torsion with mu equals 1, and this is, yes, this is like one goal of recent research. We haven't proved it, but yes, we're going in that direction. So. And finally, you want to classify triangulations. The equivalence relation is concordance, the natural equivalence relation. Namely, you have a triangulation on the cylinder, m times 0, 1, with on each end you have the 2 triangulations, then you say that they're equivalent. And triangulations then are classified by elements in H upper 4 of M with values in kernel of mu. And this you cannot replace with anything. I mean, this is the actual result, so in principle you do want to understand what kernel of mu is, and therefore what is theta 3Z, if you want to classify triangulations. All right, so this was the motivation coming from triangulations of manifolds. Now for the rest of the talk, I will discuss the methods that are being used to study the homology cobordism group, theta 3Z. So this is, the definition involves homology, 3 spheres, and also 4-dimensional smooth cobordisms. So smooth topology in dimension 4, much progress has been done using gauge theory, and there's also a replacement, Heegaard Floer theory, which is based on symplectic geometry. So there are, in fact, kind of 3 methods that were used to study this group. So the first one from the 90s is Yang-Mills theory, and this was used by Fintuschel, Stern, and Furuta to show that the group is infinitely generated. But then, more recently, this was yes, what people use nowadays more is Seiberg-Witten theory and Heegaard Floer homology. So the Yang-Mills and Seiberg-Witten equations are have a gauge symmetry, so they come from physics. And then Heegaard Floer homology uses pseudo-holomorphic curves and basically symplectic geometry, and it's actually equivalent to Seiberg-Witten theory. So in this talk, I will not discuss Yang-Mills theory, but I will discuss Seiberg-Witten and Heegaard Floer. So let me start with the Seiberg-Witten equations. This is a system of nonlinear partial differential equations. I'm not going to write them down, but they are elliptic modulo gauge, so they have a gauge symmetry. And if you impose a Coulomb gauge condition, then the system is elliptic. And they are sensitive to the smooth structure of the manifold. So you can write them for 3-dimensional manifolds and for 4-dimensional manifolds. And basically they involve a connection in a bundle over the manifold and also a spinor. And in dimension 4, they have been used to detect exotic smooth structures on 4 manifolds. What will be important for us is that in the presence of a spin structures, the equations get a pin-2 symmetry. So there is an action of this group. So this is a non-abelian group. It's made of 2 circles. You can think of it as a subgroup of the quaternions. If you write the quaternions as C plus JC, then yes, you just look like the unit circle in each copy of C, and this gives you a non-abelian Lie group. Right, and so this acts on the connection and the spinor, and the equations are preserved by this symmetry. So in dimension 3, in dimension 4, the Seiberg-Witten equations give numerical invariance, the Seiberg-Witten invariance. In dimension 3, they give homological invariance, the Seiberg-Witten Floer homologies. There are slightly different versions of this. Yes, there was a construction by Kronheimer and Mrówka in their book, then one by Freushow, one by Barcoli-Wang, and one by myself. Roughly, Floer homology means that you make a complex out of the solutions to the Seiberg-Witten equations, and then the differential of the complex is so in the coefficient, you look at the coefficient of y in del x, and that's supposed to be a count of solutions of the Seiberg-Witten equations on the cylinder, y times I, that limit to x and y at the two ends. So you can make, so you make a complex and then you take the homology, and that's called Floer homology. In fact, I constructed a bit more. I constructed a Seiberg-Witten Floer stable homotopy type. So this is roughly a space. In fact, it's a suspension spectrum whose homology is the Seiberg-Witten Floer homology. The construction is basically, well, it involves doing finite dimensional approximation and then taking the Conley index. But you can think of this space as being a CW complex, and each cell corresponds to a solution of the Seiberg-Witten equations, and then the attaching maps between the cells are characterized by the space of solutions of Seiberg-Witten equations on the cylinder between different kinds of solutions. Okay, so basically this is the input. We have a Floer homology and we have a refinement, the stable homotopy type. So now I'm going to tell you how to get invariants of homology cobordism. So maps from homology cobordism to some simpler groups. Okay, so I'm not going to follow the historical route. I'm going to tell you, like in retrospect, all the homology cobordism invariants can be obtained through something called the local equivalence group, which was defined by Staffragan. So what is the local equivalence group? Well, it's a group. I'll tell you the definition in a moment. And there is a homomorphism from theta 3c to this, and then to an even simpler group called CLE, the chain local equivalence. And the homomorphism basically takes y to the stable, to the Seiberg-Witten Floer stable homotopy type, to this space kind of where the cells correspond to solutions of the Seiberg-Witten equations. And if you want to simplify even further, you can take chains on that space with, let's say, I mean, for simplicity, we're just going to take it with coefficients in Zima 2. Okay, so now what is the definition of this group? So LE is made of spaces, or actually suspension spectra, like the Seiberg-Witten Floer stable homotopy type, but we're not going to talk about the Seiberg-Witten equations in its definitions. It's just made of spaces with a pin-2 action, and such that the fixed point set under the subgroup S1 in pin-2 is a sphere. So this is the kind of spaces that you get when you consider the Seiberg-Witten Floer stable homotopy type. The fact that this fixed point set is a sphere comes from studying reducible solutions of the Seiberg-Witten equations. So the ones that, so let's recall that pin2 is S1 union JS1. So I'm interested in the solutions that are preserved by S1, and those are called reducible. Basically, that's where the spinor vanishes, and then those are easy to characterize. So it turns out that there's just one of them. So because of that, there's a unique cell of that type, and that gives you a sphere. Okay, so that's kind of the spaces we have. And then we want to divide by local equivalence, so that if we have a homology cobordism between two y's, we get some equivalence between the spaces. So what is the equivalence? So basically, when you have a homology cobordism, what you get is maps, cobordism maps, involving that are really given by the Seiberg-Witten equations on the cobordisms. And they go from x1 to x2, and you also have a map in the other direction, from x2 to x1. They are pin2 equivariant, because we have the pin2 symmetry. And there are also equivalences on the S1 fixed point sets. So this definition is modeled on the Seiberg-Witten maps induced by homology cobordisms. And the fact that there are equivalents on the S1 fixed point set uses the fact that this is a homology cobordism, that it has a relative homology 0. Okay, so this is a group basically defined using stable homotopy theory. It doesn't use any gauge theory in its definition, it's just spaces modulo this equivalence given by having maps with some properties. And if you want, you can simplify it some more and just look at chains on the group. And I'm not going to give the definition, but it's something similar. So it's chains with some property. They have to be modules over C star of pin 2, because you have the pin 2 action. And then you have an equivalence relation, and you get some group defined algebraically called CLE. Okay, so these are good, but what we would like, is actual numerical invariance. So we want to be able to associate to homology spheres numbers, such that when two homology spheres are homology cobordant, then they give the same number. And that would give us the information, some information about theta 3z. So the prototype of this is the Floer homomorphism, which is a map from theta 3z to z. It's a homomorphism, and it actually factors through LE and CLE. And it doesn't use the stable homotopy type. It uses the Seiberg-Witten Floer cohomology of Y. So this was defined before the local equivalence group. First people had Floer homology, and Floer had a definition of delta, but yes, here I want to emphasize that it factors through CLE. So if you look at just the Floer homology, then the equivariant Floer homology, this is a module over the S1 equivariant homology of a point, which is H star of BS1, or CP infinity. And that's just f of u. It's where the degree of u is 2. So, in fact, because of the structure of the reducibles, this equivariant Floer homology looks like there's one copy of f of u, and then there's a torsion part, which is finite dimensional over f. So basically, people say there's a torsion part and there's a reduced part. And the thing that's kind of preserved by homology cobordism turns out to be the tower, the f of u. Because of the structure of the map induced by homology cobordisms, the towers are preserved, and therefore their grading, in particular, let's say the minimal grading of an element in this tower is preserved. And this is the Floer homomorphism, up to a factor of 1/2. Okay, so if you have this, then you can compute it for the Poincare sphere. There you get that it's 1. And this shows that this is a surjective homomorphism. And therefore, it shows, this is the proof of the result of Floer, that theta 3z has a z summand. If you have such a homomorphism, then you can break it into the subgroup generated by P, something that gets mapped to 1, and then the kernel of the homomorphism. And that gives you the z summand, is this thing generated by P. Okay, so this only used, the Floer homomorphism only used the S1 symmetry of the Seiberg-Witten equations. I should say so so basically the equations have a S1 or U1 gauge symmetry, and this is by constant gauge transformations. But then you can use this other conjugation symmetry, which is the J, and together with the S1, this gives you the pin 2 symmetry, and for that you need a spin structure. But on homology spheres, you always have spin structures. So we could actually look at the pin 2 equivariant Seiberg-Witten Floer homology. And that's what I did in 2013. So I constructed the analogs of the Floer invariant in the pin 2 equivariant Floer homology. In that case, there are 3 towers. Again, you look at it's a module over H star of B pin 2, and you can study the torsion and non-torsion parts. And instead of having one map, you get 3 maps. One problem is that they're not homomorphisms, unlike delta. So I'm going to draw them using this dotted arrow. But they are maps, and well, they behave a little bit like homomorphisms in the sense that when you reverse the orientation of y, alpha becomes minus gamma, and beta becomes minus beta. So there's some symmetry. And more importantly, mod 2, they give you the Ruffling homomorphism. So the Seiberg-Witten equations are related to the Ruffling homomorphism. The Ruffling homomorphism gives you the degree mod 2 of the reducible solution in the Seiberg-Witten equations. But if you just do S1 equivariant Floer homology, there can be interaction, there can be like a differential from the irreducible to the reducible. And well, in the complex, the degree is the Ruffling invariant, mod 2, but then in the homology it may not be. However, for the pin 2, because of the structure of H star B pin 2, this is no longer the case. So it turns out that in pin 2 equivariant Floer homology, the minimal degree is preserved when mod 2, when you go from the complex to the homology. Okay, so a corollary of the construction of these maps is the theorem I alluded to before, that there is no torsion in theta 3z with Ruffling invariant equals 1. And using the work of Galuski, Stern, and Matsumoto in the 70s, an implication is that non-triangulable manifolds exist in dimensions greater or equal than 5. Okay, so let's see why that's the case. So, right, so if we had a 2 torsion element, then that would imply that y is equivalent to minus y, so they are homology cobordant, so that means that they have the same value of beta, but beta of minus y is minus beta of y, and that, since beta is an integer, that implies that beta is 0. And therefore, we're using the relation to Ruffling that beta mod 2 is mu, so that gives us that mu is 0 and not 1. So basically this was known before that, I mean, yes, it's just a simple observation that to show that there's no 2 torsion with mu equals 1, you have to construct a lift of the Ruffling homomorphism to z, from z mod 2 to z, and beta is such a lift. And although it's not a homomorphism, at least it has this property that beta of minus y is minus beta of y. Okay, so I should mention that this construction of alpha, beta, and gamma use the Seiberg-Witten Floer homotopy type. Basically, yeah, you just define the homotopy type and then you take the pin 2 equivariant homology. So basically it uses methods coming from Conley index theory, but there's an alternate construction given by Francesco Lin 1 year later. So he he used the work of Kroheimer and Mrówka and defined a pin 2 monopole theory, and that's actually defined for all 3 manifolds, not just homology spheres. Okay, so far we have delta and we have alpha, beta, gamma. So this comes from S1 equivariant Floer homology, and this from pin 2 equivariant Floer homology. You can take other subgroups of pin 2. So particularly useful one is Z mod 4. So instead of looking at S1, you look at what's generated by J, and J squared is minus 1. So this gives you a Z mod 4 inside the quaternions. And then you can look at Z mod 4 equivariant Seiberg-Witten Floer homology, and then you have 2 towers, and they give you 2 new invariants called delta upper and delta lower. and they are also not homomorphisms. They're more similar to alpha, beta, gamma. And all of these invariants are about equivariant homologies, and you can get them from the chain group from the structure of the chain group of SWF of Y as a module over C star of pin 2. Okay, but if you have the whole stable homotopy type, then you're in LE. If you don't want to pass two chains, then you can apply other generalized homology theories, like K theory or KO theory. In fact, they're equivariant versions. So using this, you get other invariants. For K theory, you get 2 of them, and for KO theory, you get 8 of them. So I did a K theory version, and also Furuta and Lee have independently come up with kappa, and then John Feng Lin did the KO theory versions. And these invariants have applications to spin structures on smooth manifolds with boundary. Okay, so, I mean, you can apply other generalized homology theories, but in principle, what we would really like is to understand the structure of these groups. So this group is defined using stable homotopy types, and this is defined using chain complexes over C star of pin 2. And if we could understand these groups, then we could, we could hope to understand more about the structure of theta 3Z. For example, if we could find more homomorphisms to Z, then this would give us more and more summons in theta 3Z, assuming the maps are surjective. Okay, so that's kind of what was done with Seiberg-Witten theory. Now, in the last minutes of my talk, I will discuss Heegaard Floer homology. So this was a theory developed by Oshwart and Szabo in 2001 or later, and what it does is to 3 manifolds, it associates some Floer homology groups. There are different versions of it, but instead of gauge theory, it uses Lagrangian Floer homology on the symmetric product of a Heegaard surface for the 3 manifold. So basically, you split the 3 manifold into 2 handle bodies using a Heegaard decomposition. You look at the surface, and you take its G symmetric product if the surface has genus G. Roughly, this is, I mean, why is this related to Seiberg-Witten theory? Is because the symmetric product is the moduli space of vortices on the surface, and vortices are the dimensional reduction of the Seiberg-Witten equations to surfaces. So, but basically, you look at the symmetric product, you take some Lagrangians coming from the 2 handle bodies, and you do something called Lagrangian Floer homology, which instead of solutions to some PDEs from physics, it uses the Cauchy-Riemann equations for an almost complex structure compatible with the symplectic structure. So it uses the theory of pseudo-holomorphic curves. So Heegaard Floer was meant to be a replacement for Seiberg-Witten theory, and recently this was actually proved to be the case, I mean, in the sense that the 2 are isomorphic. So one of these groups that Oshwart-Szabo defined is the same as the Kroheimer-Mrówka group HM2, the Seiberg-Witten Floer homology group defined by Kroheimer-Mrówka, or in terms of my stable Floer homotopy type, it's the S1 equivariant homology of that. And as another group, HF hat, it's the tilde version, which is the ordinary homology of the stable homotopy type. So basically, different homologies, like ordinary or equivariant, give you different groups, give you different Heegaard Floer groups. So this is a hard theorem, so the equivalence between Heegaard Floer and the Kroheimer-Mrówka theory, there are 2 independent proofs, one by Kutluhanli-Taubes and the other by Kolangi, Gini, Honda, plus previous work of Taubes, and then the equivalence between the Kroheimer-Mrówka definitions and my definition involving the Seiberg-Witten Floer homotopy type is some joint work I did with Ty Lidman. Okay, so why do we want to replace Seiberg-Witten theory with something else? It's because gauge theory, well, it's great, but it's hard to compute. So Heegaard Floer theory is easier to compute. It's more geometric. You can sometimes count holomorphic curves, not always, but in fact, there's some work that made it algorithmically computable. They started with the work of Sharkar and Wang, who showed that their algorithms for computing HF hat in general, and then their work was simplified by Lipschitz, Oshvat, Thurston, so that HF hat, I mean, they made a different algorithm that's actually more effective. You can implement it on a computer, and yes, nowadays you can compute it for many simple three manifolds. And then for HF plus is some work I did with Oshvat and Thurston, but yes, the algorithms here are not particularly effective, but in principle, yes, the theory is computable. And these are general algorithms, but for many various classes of manifolds, they are simpler algorithms. Okay, so what can you do with Heegaard Floer homology in terms, if you're interested in the homology cobordism group? Well, first of all, you can recover the Frueschov invariant using HF plus. So HF plus is like the S1 equivariant Floer homology, so you can do the same thing. You can split this into a copy of f of u, and then some torsion part, and you look at the minimal degree, and that gives you this homomorphism delta. So you can do it this way if you want. Now, in principle, we would also like to get alpha, beta, gamma, and this was the motivation for my work with Kristen Hendricks from 2015. So there is a conjugation symmetry. It's similar to J on the Heegaard Floer complexes. And using that, we get a bunch of groups called involutive Heegaard Floer homology. And our conjecture is that this is the same as Z-mod 4 equivariant Seiberg Witten Floer homology. So that's more information than ordinary Heegaard Floer, but it's not quite, it doesn't quite correspond to the whole pin-2 symmetry on the Seiberg-Witten side, and this is an open problem to get the whole pin-2 symmetry on the Heegaard Floer side. But still, okay, so from Z-mod 4 we can recover the invariants delta lower and delta upper, which are maps from the homology cobordism group to Z, and they are more computable than the ones from Seiberg-Witten. I mean, they are supposed to be the same, but it's easier to compute, so you can compute them for various classes of three manifolds, like Seifert fibrations, large surgeries on alternating knots, or connected sums of these, following work of various people. And what this gives you is, well, one thing, it gives you more constraints on which three manifolds are homology cobordant to each other. So, I mean, if the values are different for two classes of manifolds, then you can, I mean, it follows that they are not homology cobordant. So you can show that some surgeries on alternating knots are not homology cobordant to some other ones. And furthermore, in terms of the structure of theta 3z, well, okay, we didn't get any new results, but there's an interesting new proof that this has a Z infinity subgroup. So this was proved using, I mean, first in the 90s by Fintuschel, Stern, and Furuta using Yang-Mills theory. And for a long time, people didn't know how to recover that using Seiberg-Witten. But now using this, well, using in Seiberg-Witten the pin-2 symmetry, Staffrogen give a proof. And then you can also do a proof using this involutive Heegaard Floer homology. So somehow the Z-mod 4 action is enough for that. And I gave a proof with Irving Dye using involutive Heegaard Floer homology. Okay, so, oh yeah, one thing from about involutive Heegaard Floer homology, it has a slightly different structure than the pin-2 or S1 equivariant theory. So you can ask about the analog of local equivalence, or in fact just chain local equivalence. And it turns out that there is a so involutive gives you a homomorphism from theta 3z to some local equivalence group called J, which is basically, and basically takes a three manifold to the Heegaard Floer complex of that three manifold and the conjugation involution. So what I'd like to advertise is that this group has a very simple definition. So J is made of free complexes over f of u with an automorphism iota. This is the conjugation involution, such that iota squared is chain homotopic to the identity. And then you put a condition on the homology of the complex that when you invert u, you get a single copy of fu inverse. Okay, and then you divide by an equivalence relation, similar to the one in local equivalence, that there exist maps back and forth from C to D and back. that induce an equivalence on H star on homology when you invert U. And that commute to the involutions up to equivalence, up to chain homotopies. Okay, so this numerical invariance of homology cobordism factored through this group, and so let me leave you with an open question. What is J as an abelian group? So it has a simple algebraic definition, but we don't know what it is, and it's an open problem to study it some more, and it's a current area of research. And for example, if we could show that it has some more homomorphism to Z infinity, we could hope to use it to get even more information about theta 3Z. All right, thank you for your attention.
Okay, we have time for some questions.
Homology cobordisms. Instead of integer coefficient, if we can replace any abelian group, is there any constructions, any work, known result done? For example, rational coefficient. Homology cobordisms.
Yes.
With rational coefficients for theta 3. That groups, any known result, any construction, any computation done? Instead of homology sphere.
Instead of homology spheres, if you use other three manifolds?
Yes.
Oh, I see. Yes, that's a good question. Yes, so you can study homology cobordisms between any three manifolds. Just look at cobordisms that have relative homology to either n being 0. And yes, so I didn't talk about them, but the same kind of methods can be used to study this for rational homology spheres, and in fact for all three manifolds, as long as you have the right theory. So yeah, so for example, delta lower and delta upper and alpha, beta, gamma, they exist for all rational homology spheres, and then kind of it depends on the homology of the manifold. And that again gives you abstractions about which kinds of three manifolds are homology cobordant to others.
So you've been getting a lot of invariants using various kinds of equivariant homology theories. Have you studied equivariant homology operations to get more kinds of invariants?
Oh, that's a good question. I haven't, like the Steenrod squares or something like that. Well, I guess we looked at the Steenrod squares, but in the examples we have, they are determined by the module action on equivariant Floer homology. But yeah, in principle, there should be other operations that one could do. I haven't looked into that.
Well, I had a question. So you introduced these three maps, alpha, beta, and gamma, but you only seem to use the map beta. So can you do other things with alpha and gamma?
Yes, yes. So for example, I mean, Staffregan's proof that that there's a Z infinity summoned, it uses more information than beta. I think it uses alpha, beta, gamma. And in general, I mean, you have more information, so that gives you more abstraction about which three manifolds are homology cobordant to others. Also, if you want, you can replace beta by alpha plus beta plus gamma, and that has the same properties as beta.
All right, well, let's thank Ciprian again, and we'll start again at 3:45.